Hello everyone, it's Dr. C. Happy Tuesday. Today in class we got a lot of stuff done. We almost wrapped up chapter 14, which is the acid-base chapter. We still have a few more minutes to do in terms of looking at Lewis acids and bases a little bit more, but we'll save that for Thursday. And what I wanted to do was actually get a quick start on buffers, which is the first thing we're going to cover in the next chapter. All right. So let's say you have a solution of acetic acid, and let's say it's 0.5 molar. Could you solve for the pH of that solution? Yeah, and I hope so at this point. You'd need more information, right? You would need the Ka value for acetic acid. But you should recognize this as a weak acid. It's a carboxylic acid. Carboxylic acids are weak acids. We know that acid in water is going to donate a hydrogen ion, producing hydronium and the conjugate base. Okay, so what's left after that acid donates, and that's a minus, I'm sorry. Okay, well, we'll just try to make that a little bit better. Okay, CH3COO minus. All right, so you can do that. We'd set up our ice table, solve for X, calculate pH. That's just a weak acid. But now let's say we have a solution that in addition to the acetic acid, let's say the solution also contains some conjugate base, that it contains both at the start, that it's not just weak acid. Okay, so let's say this is 0.5 molar. Let's say this is 1 molar. They don't have to be the same, so let's choose a different concentration. So now we have a solution that contains both the weak acid and the conjugate base. How does that change things in terms of a calculation? Well, let's see. Initially, if we just had the weak acid, that'd be 0.5 molar. Okay. Hydronium would be 0 at the start before the reaction started, and our conjugate base would be 0 at the start if it were just pure acid. But let's look at a solution that contains both. So initially, this is not 0. Let's say it's 1 molar. All right. Well, the first thing that's going to do, compared to just having a weak acid by itself, is in effect, we have added the conjugate base. Okay, so again, weak acid by itself, we've now added the conjugate base. What is that going to do to the position of the equilibrium? It's going to shift it to the left. So this equilibrium now is going to even lie further to the left, which will become important in our calculations. So this effect of shifting it left, we know this is Le Chatelet, but it's also called the common ion effect. We've added this ion common to the equilibrium of that weak acid, and it shifted it to the left. Okay? But we'd still set it up and say, well, some of our reactant will react. We're going to get a little bit of hydronium. We're going to get a little bit more of the conjugate base. And at equilibrium, there are our concentrations. Since I started with the acid, remember this is an acid, we need the Ka value. So our Ka is equal to 1.8 times 10 to the negative fifth, products over reactants. So far, so good? Okay. Now, if it were just weak acid, we'd have x squared in the numerator. But again, this is not just weak acid. All right, what do you think? Do you think we can make the assumption? Yeah, certainly. I mean, Ka is pretty small already. And because we've added the conjugate base, it's shifted the equilibrium even more to the left. So we know this x is going to be really small. So we're going to approximate 0.5 minus a really small number to stay at about 0.5. And what do you think about 1 plus a really small number? Yeah, we're going to assume this stays about 1. That's kind of nice because this then our calculation is greatly simplified. We have x times 1 over 0.5. Let me grab my calculator. Okay, so cross multiply. Oh, that just give us 9 times 10 to the negative 6th, right? Yes, okay. So our x is just 9 times 10 to the negative 6th molar. And what does that equal? Hydronium. Calculate the pH. And I get a pH of 5.05, I guess, if we round up. Okay? That doesn't look so bad. And guess what we just calculated the pH of? Yeah, this is a buffer. And we'll talk about in just a second why this is a buffer. All right? So calculating the pH of a buffer is pretty much like calculating the pH of a weak acid, except you're going to have the conjugate base present at the start. And the cool thing is, your assumption is always going to work because you've shifted the equilibrium even further to the reactant side by adding that common ion. All right? So that's calculating the pH of a buffer. Now, what do we mean by a buffer? What is a buffer? Well, so let's define that. A buffer. It's going to be a solution that resists change in pH, and that's resist, I apologize, in pH when a small amount of acid or base is added. Okay, so again, a couple of key words here. When we add some strong acid, now usually we say strong acid, so strong acid or strong base. Doesn't have to be, but let's just say strong acid, strong base. So we're going to add strong acid or strong base to that buffer. The pH is still going to change, but it's not going to change as much as we would think. So the solution resists change in pH when we add a small amount of strong acid or strong base. Okay? So we need to be able to add either acid or base to that buffer, and it has to resist both. So to resist strong acid, what do we need in solution? Yeah, we're going to need a base to react with that strong acid. And if I add strong base, what do I need to react with that strong base? I need an acid. So a buffer has to have both. It has to have both an acid and a base. All right? And it turns out they have to be, it just can't be any acid or base. It turns out they have to be related. And if we, related, that sounds kind of odd, right? They have to be siblings or something. But they have to be related in the sense that they need to be a conjugate acid-base pair, because what's going to happen if we react one of those components, say I add strong acid, it's going to react with the base, it's going to produce the acid part of, it's going to produce the conjugate acid. So if I add strong acid, the conjugate base part of the buffer is going to react and produce the conjugate acid. So they need to be a conjugate acid-base pair. I didn't say that well, but we will talk more about that in class as we see how the concentrations change. So a buffer is going to contain, and it has to be a weak acid and a weak base that are a conjugate acid-base pair. Okay? And the reason why it has to be a weak acid and a weak base is because if I had a strong acid, its conjugate base is so incredibly weak, it's not going to function as a base in water. So I wouldn't have both. Okay, so it has to be a weak acid and a weak base that are a conjugate acid-base pair. So what we have up here, that would suffice. We have acetic acid, all right, weak acid. Its conjugate base, acetate, is a weak base. That will be a buffer. And we have to have concentrations of both of those present at the start of the reaction. All right? So, pretty cool. You now know what a buffer is. You now know how to calculate the pH, because it's really not any different than calculating the pH of a weak acid, right? Now let's do one more thing for this pre-lecture. So know the definition of buffer, resist change in pH when we add a strong acid or strong base. And that's because it contains both a weak acid and a weak base that are a conjugate pair. This ice table, let me scroll back up, should look no different to you other than the initial concentration there of the conjugate base. Solving for the pH is pretty easy. And the very last thing for this pre-lecture, let's consider, well, actually two things, but one main thing and one minor thing. Let me write down a couple of formulas here. Would that be a buffer? Yeah, right? This is a weak base. You should recognize ammonia as a weak base. It's an amine. Ammonium is its conjugate acid. Okay, the conjugate acid of that weak base. So this is going to be a weak acid. Okay, so a weak acid and a weak base that are a conjugate pair. That is a buffer. All right, so if we set this up, when we write these reactions, you could start with the base in water and produce the acid, or you could start with the acid in water and produce the base. I always like to start with the acid part of the pair, the one that has one more H+, because then I know one of my products is hydronium. It makes it a little easier to solve for pH. So that acid in water, again, donates an H+, producing hydronium, and then the conjugate base. So there's our two parts of the buffer. And if we wanted to solve for the pH of this buffer, we'd have to know the initial concentrations of each one. We'd have to know, what we had. Is this 0.1 molar? And is this 0.25 molar? Whatever they are. And then we would write those in. So let's just do what we have. I'm not going to solve this one. Okay. And hydronium would be 0 before it starts. And we do our same thing. Not so bad. All right, last thing. I promise this is the last thing. Does NH4 plus or acetate CH3COO minus, do those exist as pure substances? Can I just go over to the lab shelf and get those? No. They have they're charged species. They're going to be combined with something of opposite charge. Okay? So where are we going to get either acetate or ammonium? Where are they going to come from? What have we just been covering? Salts. They're going to come from salts. So usually at least one component of your buffer is going to come from a salt. So you'd probably see a problem, and it might tell you have a buffer that is NH4Cl with ammonia. Okay? That shouldn't cause too many problems because that's NH4 plus and Cl minus. We know Cl minus is the conjugate base of a strong acid. That's not going to have any base strength in water. That's not going to affect anything. But we're going to have our conjugate acid-base pair. Same thing for acetic acid. We might combine that with sodium acetate. And there's our salt. And this salt contains the conjugate base of that weak acid. So don't be confused. Typically at least one component. We could also have a buffer that both components could be salts. And we'll see one of those in class. Okay? But since those are charged species, NH4 plus or acetate CH3COO minus, I can talk, they're not going to exist as pure substances. So those are going to come from salts. But again, watch for the two components, weak acid with its conjugate base. weak base, in this case ammonia, with its conjugate acid. You need both things present, a weak acid and a weak base that are a conjugate pair. All right, that's a brief introduction to buffers. We will do a lot more in class on Thursday. It'll be buffer, buffer, buffer all day long. So much excitement. But I will see you on Thursday. Take care.